All right, let's start looking at some proofs for properties of union, intersection, and relative complement. And this is the first one I'm going to look at. It's part of Theorem 29. So I recommend when you're reading a proof or when you're looking at a proof in lecture, when we reach this point, pause the video and think about, you don't have to write anything down, but just think about what would you do? Allow yourself to become stuck or to have a guess at least as to what you would do, and then unpause. Okay, so here's my first observation is I'm proving an equality. That's the kind of thing I'm proving. So what do? Well, the main things available to me for proving equalities are Axiom 8, or more commonly we use Theorem 10. Actually, it's much more common to use Theorem 10. The reason for that is that Theorem 10 breaks things down so that proving your equality becomes a matter of proving two parts. And usually, in practice, each of those parts is manageable on its own, but trying to prove a double arrow all at once is difficult. So this actually is one of these rare situations, and almost all of the parts of Theorem 29 are part of this rare situation where actually Axiom 8 is useful directly. You can get this double arrow directly. So here's what I mean. So if our goal is to prove that these two things are equal, not A and B, but this and this, then our goal is to prove that for all z, so goal is to prove that for all z in there, if and only if z in there. So consider any z. And since I'm proving a double arrow here, I'm not going to say consider any z and then assume this side and then prove this side and then I'll be done. It's not like that. So that's why I'm not just saying consider any z in there. I'm not merging those first two sentences there like I usually do. I'm just saying consider any z, and z is arbitrary. It's just an arbitrary thing with no other assumptions about it, and then I have sort of two directions to prove, right? So normally if I do this and I have these two directions and I prove them on their own, then this would be better to organize as a Theorem 10 style proof, since it already split up the equality into two directions. It's really just proving two inclusions. But I'm actually not going to do it this way, and that's why I'm going for the Axiom 8 approach. So I'm going to say, so how can I prove a double arrow statement without proving both directions? So I'll show you. We have z in there if and only if now Axiom 5 provides the double arrow here, right? So something is in a set if and only if the membership condition holds. So this double arrow is this double arrow. Z is in there if and only if, and now I need to break down what it means for z to be in there. So let's see. Sorry, let me reserve this whole area here for scratch work, which I'll erase in a moment. So A union B, that's the set of, let's say, x such that x is in A or x is in B. So I have to use the definition of union somehow in my argument, right? Now z is in A union B if and only if z is in this. And what does it mean for z to be in this? So I have to use Axiom 5. That means I take this proposition here. Sorry, I take this proposition here, and I've made the bound variable here green. And what I'm going to do is replace the green thing by z. So z in A or z in B. That's what it means to say z is in here. Z is in A union B if and only if this proposition here holds for z. So that's Axiom 5. Okay. z in A or z in B. And there I've used the definition of union. So that means I'm using definition 28 part 2, this, and I'm using axiom 5. Okay, so this is how we can get a double arrow without having to do both directions, is axiom 5 provides a double arrow. We can also get double arrows from certain aspects of logic. So let me get rid of this. We can remember what the goal is. If you have an or, like phi or psi, then you can flip the order and you'll get an equivalent proposition. So that's from logic, and I don't need to reference anything when I do that. We never reference the logic rules that we use, typically. We just use them. So I can flip things around, and then I've written something that, by axiom 5, is the same as this. So here's axiom 5, powering this arrow. Here's logic. And here's axiom 5 again. And if I have a chain of double arrows starting somewhere and ending somewhere, then there is transitivity for double arrow, which tells us that the first thing is equivalent to the last thing. The first thing double arrows with the last thing. So that's it. Then we've reached the goal. For an arbitrary z, we've shown that for z to be in here is for z to be in here is the same. And by the way, when I say this is by logic, this double arrow here, that lets you flip the order of the or statement, what I'm referring to is way back when we introduced the or statement, we say the order does not matter, so we consider this and this to be the same. At the time we introduced this, we had not said what it means for two propositions to be the same. The double arrow doesn't get introduced until later in the notes. But now that it has been introduced, we know that what this is really saying is actually we have a rule that says that phi or psi is true if and only if psi or phi is true. So this is really nice and short, and you will find the same thing for most of the other many parts of Theorem 29. But I want you to think of this as a very rare thing to happen. It's very rare to be able to just build a chain of double arrows like this, starting from one thing, starting from z is an element of one thing, ending with z is an element of the other side. This is a rare way to be able to prove that two things are equal. Typically, much more typically, if there's any kind of complication to the setup, if it's not so simple like this, typically you have to show one inclusion and the other inclusion following different lines of reasoning, following steps that don't always work both ways. And so it makes a lot more sense to use, in those situations, it makes a lot more sense to use Theorem 10 approach rather than the Axiom 8 approach.